They didn't say it.
How many
but,
sick days do you really get?
like a lot. But I only use 2 or 3 a year, if that.
They carry over some. The first year they carried over to next year. Because they messed up all the, no one recorded who had time off and did and what it was for the first year of school. So.
Oh, yeah, but that was different because I had like PTA, like an outrageous amount of PTO time.
Yeah.
What's that?
Paid time off, so like just taking the day, like vacation day. Or like, we only get 2 days of vacation, like 2 days a week can actually just intentionally take off.
And
But like someone who normally works would get like 3 to 4 weeks of vacation, but we get the whole summer off, so like,
yeah.
and you know, various days off throughout the year.
Other than other unpaid,
Yeah, I mean,
other unpaid would be Christmas break off.
not a full week and a half, so.
Yeah, Christmas Day.
And
We also had
your,
We also had every Friday off last month.
That's the only thing with that.
like, usually they get like the day and maybe another day, but most of the time they take, if they
My
don't
dad-
go to work, they're using vacation.
My dad, he gets Christmas Eve to New Year's off. Not taking paid TTO. He always gets that off.
Where does he work?
His boss, Snyder Associates, they're city engineers. But his boss doesn't want to come in. That's why.
So
His boss is like a family reunion in like Florida every single year for Christmas. So his boss doesn't want to come in to get the whole department.
Lucky here.
Yeah.
So you only work 180 days a year.
He gets less PTO and his
Oh,
boss
what?
PTO.
Work 180 days a year.
Probably.
Well, I mean, you work more because, yeah, as a teacher, I mean, as a teacher.
Yeah. But I typically work more than 40 hours a week. Teachers work more than your typical weekly hour. It's always something to do. Anyways, so we're moving into chapter 10. Chapter 10, intermolecular force chapter, talking about, I think, solids and liquids a little bit as well. But predominantly intermolecular forces. You should recall some of this stuff from last year. Okay? Yes? Maybe? Looks a little familiar? Okay. Okay? If you remember, we talked last year about the word intra and the word inter. What does the word intra mean? Within. And the word inter means like interstate is a highway between states. Intersection is a road between another road. I never really thought about that one. Okay? So when we're talking about intermolecular, then we're talking about a specific type of force here. So an intramolecular force would be the forces that are within the molecule. That would be, what would be the forces within the molecule then? What is it referring to when it says the force within the molecule?
The bonds.
Yeah. So these guys are your intramolecular. Now, any bonds of anything that we've been dealing with up to this point are your intra. They're the things that hold the molecules together. Right? Then there are intermolecular forces, and it says between. So between what? What is it between? Okay, that's what creates the force, but what are they between? Yeah, two different compounds or molecules. It could be the same kind of compound or molecule, but two separate molecules. Like a water molecule and a water molecule. What holds them together in a liquid state? It's the intermolecular forces. Okay, now, Andy went a step further and started talking about partial charges and polarity. That's what leads to these things. Okay? This should also come back to you guys a little bit. It's important that we realize that when substances like water undergo a phase change from a solid to a liquid to a gas, that the molecule remains intact. What do I mean? Yeah. So when I take water and I go from a solid to a liquid to a gas, does this change at all? No. The intramolecular forces don't change and your water molecule stays intact. So what is it that is changing? That's true. Energies are changing, and then when you go from a liquid to a gas, what gets severed? The intermolecular forces. Okay? So let's just kind of go back a little ways here. Let's just talk about HF. Let's talk about, okay, how do these intermolecular forces come about? Okay? These two guys have different what? Yeah, I could have been a lot of things, right? They have different electronegativity values. Those different electronegativity values create what? Polarity. Right? So which one's more electronegative? Okay, so we're good at knowing where the negative and the positive side is, correct? Where's the negative? Okay, polarity is created due to differences in electronegativity values. Okay, well, how does a water molecule get attracted to another water molecule, or a hydrogen fluoride molecule get attracted to another one? Well, these opposite charges attract each other. Okay, so the negative side of one molecule attracts the positive side of a different molecule. So, what would we call this? Intra. What would we call this? Inter. Which one's stronger? It better be intra. If inter was stronger, why would, when you go from a liquid to a solid, or from a solid to a liquid to a gas, why wouldn't the molecule itself just break before you break the intermolecular forces? Does that make sense? Okay. So, because let me, I think I got some numbers here. To take 1 mole of H2O and to vaporize it, what process is that? What's vaporization?
Vaporization.
Yeah, what is it? What is vaporization? Guys!
It's like gas to a liquid.
That's
Or
condensation. Liquid to a gas. Okay. Liquid to gas.
It was too simple of a question.
Okay, sorry, I can't do any simple questions anymore in this class, can I? Okay? So that's how much energy it takes for me to take a mole of water and to go from liquid to gas state. It's kind of a lot, right? 40 kilojoules. How about the amount of energy needed to break a mole of hydrogen-oxygen bonds in H2O? Big difference. What's stronger? Which one's inter, which one's intra?
Is that how much it takes to break?
Yeah, that would be how much energy we needed to break that bond and that bond. So it would be that divided by 2 would be what our bond energy was for OH. You guys remember doing bond energy for OH? So it would be like, take that divided by 2, what is that, 467 or something like that? Okay? So you can see, to break the bond between, or sorry, within, takes way more energy than to break the forces that hold them in a solid or liquid state. Right? Okay. So, intra, inter. Intra is within, inter is between. Which one's stronger? Intra, okay, because you have to break the bonds that hold the molecule together, versus this partial charge that can be strong depending on the bigger the difference, the stronger it would be. Okay, so let's talk about the three types. Oops. There's some random vocab word that you may or may not see in your test. Does that vocab word make sense based on common sense? What does that mean? Yeah, it's like a compressed state, condensed, you can call it the same thing. Okay, and what do we know about solids, liquids versus gases? Yeah, solids and liquids are very heavily compressed. Okay, all right. All right, first type, and again, you have seen these three types before. Okay, first type, dipole-dipole attraction. It's the attractive force resulting when polar molecules line up so that the positive and negative ends are close to each other. That's what I just drew, this HF over here. That's not true. It's not true. Let's say it's HCl, and I'll explain why it's not HF. What'd you say?
Because I remember like the NOF being split.
Yep. Ah, I did F again. Ha! Okay, this would be a dipole-dipole attraction. Okay, and we'll talk about how dipole-dipole and hydrogen bonding are very similar here in a second, and I'll clarify why I changed it to chlorine and from fluorine. Okay, so your normal polarity that gets created, and this polarity that creates the attractive forces here, the intermolecular force, is a lot of times just your dipole-dipole. Okay? Well, there's not a whole lot I really need to stay up to date on this. However, I do want you to turn to page 441 in your books. So the top left corner, you can kind of see, I said I would represent the HCl up there pretty well. You can see that there's red dotted lines and blue dotted lines representing attractive forces and repulsion forces. So what happens with these guys in the solid and liquid state? Now, solid state, they're held much more rigidly in place. Liquid state, they have the ability to flow, right? Okay? But really what ends up happening is you try to maximize your attractive forces and minimize your repulsion forces. Okay? Because you're not going to be able to get completely away from having zero repulsions. That's not possible. Does that make sense? There will be repulsions within these guys. Okay? But if you can maximize your attractive forces and minimize your repulsion forces, that's your most stable arrangement. Make sense? Okay? Okay, then there is a specific group, which is really just a stronger version of a dipole-dipole, and that's why I kept the F out. Okay, and it's known as hydrogen bonding. You guys should remember this at least a little bit. You said you remember NOF, NOF. Okay? Okay, so it's a little bit stronger dipole-dipole attraction, and they give it a different name because of it. Okay, they call it hydrogen bonding. That's when hydrogen is bonded to one of the three most electronegative elements on our periodic table, NOF, or what I would just abbreviate as NOF. Okay? Now, this should make sense. As these electronegativity differences or electronegativity values get further apart from each other, the stronger this is. Does that make sense? Like if I have HF, what, that's 2.1 electronegativity, that's 4.0, 2.1, and I don't know, 3.0. Okay, the bigger difference in pole, the more charge displacement you're going to get. The more charge displacement, the stronger that charge will be, and thus the stronger that will be attracted to each other. That makes sense? Okay? So really, hydrogen bonding is simply just a stronger version of your dipole-dipole attraction. Now, be very, very careful. Let me try to find an example. Something like this. If you were just looked at this, you might think, oh, it has hydrogen bonding. No, it doesn't. Here's why. Because what is it bonding with the hydrogen in the fluorine? Carbon. Okay? So when we're talking about hydrogen bonding, we're specifically talking about a bond between hydrogen and fluorine because they're the two biggest differences that you're going to get on the covalent scale. Okay? And oxygen and nitrogen are your next two greatest differences. Right? Last one, which is the most intriguing, I think. Because we do have to somehow deal with these nonpolar guys. Remember those fun ones? Like, let's say, fluorine molecule. Or methane. Both of these two molecules exist in what physical state do you think? Naturally. Gas. Okay? Does that mean it is impossible for me to get this in the liquid or solid state? No. We can do it. Okay? So the question is, I don't remember which, I'm guessing that's the more electronegative one. I can't remember off the top of my head. So if every side of that molecule is positively charged, how am I going to get another CH4 molecule to be attracted to a neighboring CH4 molecule? Because last time I checked, positives and positives don't what? They don't track, right? So let's look at this definition. It's quite an interesting guy here. It says the forces existing among noble gases and nonpolar molecules that involve an accidental dipole, which induces a momentary dipole with a neighbor. So your book's open still, right? Next page. 442. Okay. Look at the visual there at the bottom. Okay, I think there's a couple assumptions that we a lot of times make. Okay? Although we assume that electrons in an atom are uniformly distributed around the nucleus, this is really not true because electrons are moving rapidly, very fast. So do you think that at every given moment you're going to have a perfect electron distribution that'll keep it completely nonpolar at all points and all times? Think that's possible? Do you think it's possible for maybe an electron or two to maybe get a little bit of out of place, just due to sheer entropy? Possible, right? Okay, so if you look at the little visual at the bottom there, okay, you can see atom A and atom B, no polarization, nonpolar. Okay, then you can see the next little visual down. It appears that some of the electrons in A started to shift a little bit just due to random rapid motion. Okay? Which created a temporary what? Dipole. Do you see the negative end of the molecule, or the negative end of the atom and the positive end of the atom? Everyone see it? Okay? Well, if you have two atoms next to each other, and one has a partial charge, what ends up happening is the one with the partial charge induces a charge on the other guy. Alright? So you can see in the visual on the very bottom, you see how atom B, its electrons shift towards the positive end of atom A. You see it? Okay? Now this is called London dispersion. Okay? If you cool certain compounds down enough and their electrons get displaced to a certain extent, you can create an accidental dipole. Now this right here is the weakest. Okay? It's not naturally going to just have its own dipole. It's an accidental created dipole due to just sheer randomness of electrons being not perfectly uniform. Does that make sense? Okay? This is the strongest. Okay, this is the most difficult simply because you can actually get one that has London dispersion forces that can be actually fairly strong. In fact, there are some London dispersion forces, guys, that actually are stronger than that. And I'll explain why here in a little bit. Okay? Now, here's something I want you to, I don't know if you actually have it in your notes or not. Oh, I didn't give you much for notes on that section, did I? Okay. So, here's what I want you to write somewhere next to London dispersion forces. There are some factors here that become important. The bigger the molecule, now I'm specifically talking about London dispersion here, it's going to lead to a higher BP, which is representing boiling point. Because of stronger intermolecular forces. Okay, so this should make sense. The stronger the intermolecular forces, the more energy you would need to break that force to get it to become a gas. Does that make sense? Let me state that again. Right? If I got HF, okay, this attractive force there, the stronger that force, the more energy you would need to break it to get it to become a gas. Right? Well, isn't that what boiling point is? Okay? The higher your boiling point, the stronger your intermolecular forces. Now, how does this apply to London dispersion? Because I specifically said the bigger the molecule. Why does a bigger molecule that's nonpolar give you a higher boiling point? I guess what I'm asking is why does the bigger molecule make this a stronger force? Any ideas? Okay, you're on the right track. It's kind of one that you might think is overly difficult, but it isn't as difficult as you think. Don't overthink it. Okay, but we're specifically talking, because this does not affect these two that nearly as much, but it does this one. Why does a bigger molecule make the dispersion force stronger? Here's your answer. More electrons. The bigger the molecule, the more electrons you have, the more unequal displacement or accidental or temporary dipole that gets created, and thus the more shift of electrons and the stronger the force. Does that make sense? Okay. Now, there are a few things in here that we didn't cover. Surface tension, capillary action, cohesive, adhesive. That's all reviewed from physical science and chemistry. So I'm going to assume that you can read about those. I'm not going to discuss them anymore. Okay? Questions? All right. Well, it got really quiet since